In this video, we'll be talking about sampling a sensor. The idea behind sampling a sensor is checking the value of that sensor. Now, we could do that with our eyes. For example, you look at the thermometer and say, oh, it's 23 degrees or whatever it may be. But we'll be taking it to the higher tech approach and using an analog to digital converter to get those analog values that our sensors actually giving us out into a digital value that our microcontroller or microprocessor or computer can actually understand. Now, the reason we need to do that is these sensors are sensing physical variables in the analog domain. We see the picture up the top there. Our physical variables, pressure, temperature, humidity, acceleration, pressure, whatever they may be, they're all continuous values that we're trying to measure. It might be, our temperature might be 24.3215, whoever knows what degrees. And we need to quantize that. We need to bring it into the digital domain and say, okay, our temperature on a scale of 1 to 100 or 1 to 1023 or whatever scale we're looking at, we'll be talking about that in a moment, is 52 or 38 or whatever it happens to be. We need to quantize it and put it in small digital buckets that we can understand quite easily. The thing that we use to do that is called an analog to digital converter. So it converts that value, for example, from our sensor output of 1.25 volts that we've got there to a value in the range of 0 to 1023, where 0 might be 0 volts and 1023 might be 5 volts. So in that range, if we consider that voltage within that range of 0 volts to 5 volts, and 5 volts being 1023, well, the value that's understood by our analog to digital converter would be 256. There's some pretty basic ratio-based maths to figure that out. Now, when we're thinking about analog digital converters, there's two important things to consider. One of them is the range, i.e. the range that analog to digital converter input can operate over. And the other one's the rate, i.e. how quickly do we actually perform our samples. Firstly, the range. We need our analog to digital converter to have at least, at the minimum, the same range, probably larger than the range of the sensor that's actually connected to it. So if our sensor gives us data in the range of 0 to 5 volts, our analog to digital converter can't have a range of 0 to 3.3 volts, for example, because it's insufficient range to read the full scale range of that sensor. So we just want to make sure our range is sufficient there. But that leads us to the next question. How quickly or what frequency do we actually want to sample our sensor at? How often do we want to do it? And the answer is, well, it really depends on how quickly the sensor data is changing. For example, think about the different types of sensors that we've got here. A weather station. How often do we need to measure temperature? Well, we probably don't need to measure temperature every 10 milliseconds, for example, because temperature is not going to change that much, or at least if it is, something's seriously gone wrong. Maybe measuring temperature every 10 minutes would be sufficient, because that gives us a pretty good representation of how temperature is changing. Maybe every 1 minute. That'll give us a significantly better representation. What about if we've got a ruler that we're trying to vibrate, we pull it down and vibrate it, and we're trying to measure what the frequency of that vibration is? Well, clearly we can't sample that ruler, however we're doing it with a strain gauge or with a camera, every 10 minutes. We're not actually going to see that vibration. So we need to sample it faster than what it's actually vibrating at. Or what if we've got a wheel that's rotating, for example, on a car, and we're trying to measure how fast that car's going? Do we need to measure it every nanosecond? Well, probably not, because if our car's traveling that quickly, something's probably gone wrong. But do we need to measure it every 10 minutes? Well, that's not going to give us an accurate determination of speed, because the wheel's probably turned thousands of times in that 10-minute interval, unless it's parked somewhere. So, how quickly do we measure? Well, the minimum rate we need to measure is twice the rate of the highest frequency that we want to measure within our signal. So if our wheel, for example, is turning 100 times a second, that's the highest rate that our wheel's going to turn, we need to measure it twice that rate, 200 times a second, or 200 hertz that we're going to measure at. And that's how we can avoid any loss of information or corruption of the signal. Also called, we'll learn about it soon, aliasing. Now, this has been known for almost 100 years. Harry Nyquist was an engineer that developed this Nyquist theorem in 1928. And so all we need to remember, according to the Nyquist rate of sampling, we need to measure at twice the maximum frequency within the signal that we're expecting. Now, why do we need to measure at that? Well, let's have a look at a few examples of both undersampling and then sampling at the Nyquist frequency and oversampling. So here we have a frequency input, F in, of 5 kilohertz. And if we undersample it, we measure at 5 kilohertz. Have a look what's happening. We measure along that sine wave at 5 kilohertz intervals, and look what the result is when we put a straight line through all those values. We get a flat line. It looks like that we don't have a sine wave here, but we've got a flat waveform at maybe like a volt or half a volt or something like that. And so our frequency that we've digitized, when we've converted this to a visual value and said, what frequency input do we have here? 0 hertz. It's just a flat line. Hang on a sec. Something's gone wrong. We've lost it all. Okay, let's undersample it, but undersample it a bit faster. So not at the same frequency that it was dealing with there. So here we'll sample it at 7.5 kilohertz. So 50% faster than the actual signal itself. And you'll see what we do is we're sampling at a whole lot of different points along that sine wave we have there. And when we actually digitize it, we look at our frequency that we've retrieved there, and it's now 2.5 kilohertz. That's interesting. We've actually got this alias sort of effect occurring where if we say 10 kilohertz minus 7.5 kilohertz, it actually gives us 2.5 kilohertz. And that's what we think our digitized frequency is operating at. That's no good either because we've corrupted our signal and we've lost our data integrity. Let's move up to the Nyquist rate where we're sampling at twice the maximum frequency, i.e. 10 kilohertz within this signal. What we do there is we can reevaluate or we can recover the value or the signal that we had there. We had 5 kilohertz in, we've got 5 kilohertz out when we've sampled at our Nyquist rate. But sampling at the Nyquist rate is the minimum rate that we want to sample at. We can oversample. So we can sample, for example, at 20 kilohertz. What happens when we sample at 20 kilohertz? Well, we've got our correct digitized frequency of 5 kilohertz, but we've actually represented all the peaks and troughs a whole lot better in terms of amplitude for our digitized frequency. Having said that, that's about as far as we'll get into the nitty-gritties of analog digital converters. If you were studying the digital electronics subject with me, we go into a whole lot more detail about actually programming these and using these within our digital system. Here, we're just trying to act as a bridge to get from the analog domain to our digital domain so we can get that data on our computer into MATLAB and use it for something useful.